Hello, I hope you are doing well. Today, I would like to present a very mini lecture about solving an optimization problem into the GAMS software. The focus of this presentation is how we can code and apply the GAMS software for solving our optimization problems. So let's start. This presentation is an introduction to the GAMS software for solving optimization problems. In this presentation, I will first define and also introduce the base papers. And based on these base papers, we focus on a classical optimization problem, which is Generalized Quadratic Assignment Problem, which is a very classic and complex optimization problem. And then we coded the GQAP into the GAMS software, how we can implement this problem to the GAMS, and how we can uh, how we can do the sensitivity analysis for the key parameters. So the base papers referring to the two of my recent papers where my co-authors and I proposed new solutions for solving a generalized quadratic assignment problem. And now the definition of a generalized quadratic assignment problem. Uh, this problem can be considered in a manufacturing system or supply chain system, where we want to allocate a set of equipment units or products to a set of production centers or facilities. In this optimization problem, we have defined two indices for the production centers where indices I and K uh, are belonging to the set I, where we have M production centers. And we have two indices for the equipment units where indices J and L referring to the set J, where we have N equipment units. Uh, there is an assignment cost which define the amount of cost for the assignment of an equipment to a production center. And based on geographical point view for a supply chain system, there is a distance between these centers that between these centers of for these facilities or centers, we have a distance matrix that we this shows the geographical distance for between two different production centers. And we have a flow uh, that shows that how each equipment is has a relation with another equipment. So these the equipments are linked, and there's a flow between the equipments. And we have an interaction cost, which is a quadratic cost, which refers to that fact that um, you know, two different assignment, the assignment of and a production center to equipment, and also another one for assignment of different equipments to the production centers. There is an interaction cost. This cost is linked between the distance and the flow of the distance of the facilities or production centers and the flow of the products. So if we assign uh, equipment to a production center, if we assign another equipment to another production center, there is an interaction cost, which is a complex cost which must be considered, has been and have been considered in this optimization problem. Two important parameters of the GQAP are the first one are the space required for the installation of an equipment at a production center. Doesn't matter how much space we need and how much the capacity that we have. So for assignment of an equipment to a production center, there is a space which is needed, and for each facility, facility that there is a limitation for the total capacity. So we have these two parameters. And finally, the decision variable here for this optimization problem is that we want to assign which equipment to which center. So the main decision variable here is xij, which is a binary variable. And based on this variable, we will have an optimization problem. This optimization problem is a nonlinear integer programming. The only variables we have is a binary variable here in the equation number 4, which is the assignment variable. And the objective function here has two terms. The first term is the classical assignment cost, which refers that if an assignment has been done, there is a cost associated to this assignment. And there's an interaction cost, which shows that if two different equipments have been assigned into the two different or the same two different for the assignment of two different equipments into the two different factories, that based on this assignment there is a quadratic cost. So we have an objective function which aims to minimize the total cost, including the assignment cost and the quadratic cost, where this quadratic cost is nonlinear due to the multiplication of two binary variables xij and variables xkl, which shows two different assignments of equipments to the production centers. We have constraint 2 and constraint 3. Constraint 2 shows that each equipment must be assigned to only one factory. It means that if an equipment is assigned to a factory, it cannot be assigned to another one, and this is unique. It also means that the equipments are not splittable, and each equipment must be assigned to only one factory or production center. And constraint number 3 shows that the limitation of each factory is limited. It means that if we have assigned a set of an equipment to another factory and a set of assignment have been done to a specific factory I, this factory must have a feasible capacity for these assignments. So we know that the facility or the production center must be able to have efficient and enough capacity for the assignment to support the spaces needed for these assignments. So based on this optimization problem, we now need to reformulate it because we have a nonlinear term. This optimization problem cannot be solved in commercial software such as GAMS due to this nonlinear term. So note that this optimization problem has n plus m constraints based on the constraint number 2 and constraint number 3, and we have nm variables, which are the binary variables that we will have. To make this problem and this optimization model linear, there are many ways. Here we follow the most efficient one, which was taken from the base papers that I showed to you. Consider that we can define a new variable which is called yijkl, which represents the multiplication of two variables. For these two variables which are multiplicated, we can define a new variable. Since we know that the result and the value for the xij xkl is the same as xkl xij, so we know that we can have the meaning that the variable yijkl can not only represent this value but can also represent this value. So we have two different variables which have the same meaning and same value. Now we are defining a new constraint. In constraint number 5, we multiply the assignment constraints into the variable xkl. Since xkl is a value which is non-negative, okay, so we only it is multiplied, and we have the same a new that have this multiplication, which we can be represented by the variable yijkl, and since yijkl is the same as ykl we will have two new constraints. To explain it more, consider that the equation number 2, where we have the sum on I for variable xij equals to 1. Now we multiply both sides of this constraint into the xkl, and then we will have two new constraints. Well, we use these two new constraints to provide a link between the new variable yijkl and the nonlinear term xij xkl, where this variable translates this multiplication of two different variables. Based on this, we have a linear generalized quadratic assignment problem, which is taken based on my paper, where the objective is the same as before. However, instead of multiplication of two variables, we have one new variable, which is non-binary, and we consider the constraints from the generalized quadratic assignment problem, and the new constraints which over the constraint number 6 and number 7, and these new constraints are introduced to provide a link between this new variable and the multiplication of xij and xkl. So now this mixed integer programming model, which is linear, and we have both integer variables such as the assignment variables x, which are binary, and the non-binary variable, which is the y or y ijkl. We now can solve this optimization problem using the GAMS software. So now we want to implement this linear optimization into the GAMS software. In this regard, I took an instance from my papers, which includes 15 facilities or production centers and 20 equipments or products. In the GAMS software, we must first define the sets. So we have two sets, as I explained before. The set I, uh, I, which is refers to the set which is belong to set I capital, and we have used the function alias, which shows that the I has another sister index where both I and K are uh, two different indices which are belonging to the same set. And another one is for the index J, where the indices L and J are belonging to the same set for products. Now we want to define the parameters. For example, for capacity of the factories, if we have 15 factories, or if we have 15 production centers, we assume that the capacity are defined like this. Uh, for the rest of the variable, let me rest of the parameters, since other parameters will be which has two dimensions, so it is difficult to define it uh, based on in the PowerPoint. So in addition to the parameter bi, no, here the name of the parameter is b, and we use parentheses and the index I to define this parameter. And after that, we have the variable, the parameter C, which was the assignment cost, as we have in the original optimization problem, Cij, which we use the table because it is like a table where we have 15 rows, and note that we have 20 equipments. So for the table Cij, we define this the values of these parameters like this in GAMS software using table. And similar to the parameter Aij, which is the space needed for the product to be installed at a facility or production center. Here is the same, where we have the rows are representing the facilities or the factories or the production centers, and the columns here are the for the equipments. And we have a table of distance, which shows the distance between two different factories or facilities. We have this table has 15 rows and 15 columns, which shows the distance. And we have the another variable, another parameter is the flow between the products, that shows that it will be a table with 20 columns and 20 uh, rows, 20 rows and 20 columns. And after this definition, we can now define the variables. So we have the variables here. The variable Z is the total cost, and the variable Q, which I use here, is the same as Y in the paper. this variable is a non binary variable, and we know that the variable q here is positive, and the variable x is the assignment for the equipments to the factories. And now we need to define the objective function and the constraints for this optimization problem. So we use the term equation. We first write it, and then we write the name of each equation. So the first one I call it objective, and the rest, the constraints, are numbered as E1 to E4. So here the objective, after the objective, we wrote 2 points, and then we wrote the Z. This means equality. It means that Z equals to the sum for the first term in the objective function and the second term. And we have the assignment constraints where we in E1 for each J, where there is a summation on I for variable xij, which is equal to 1. And for another equation is for the capacity constraints, where it shows that for each I, for each factory I, we have after 2 points, we have the sum, which shows that for all j, for the variable xij, which is multiplied to aij, it must be lower than to the capacity. And these are the two new constraints, as we have in the optimization model, which shows the link between this new variable and the assignment variable. After this definition, we need to write a name for this model. So we call it a name for this model, and then consider that we want to run all the equations, and we can define the options. For example, this is a MIAP, and I want to use a CPEX solver, and also we want to have a limitation time as 3600 as a time limit, and we want to solve this model using MIP, minimizing the variable Z, and we finally want to get the report for the variables X and variables Z. So now let me we can now run this optimization problem, and as we see that how the GAMS is searching for finding the optimal solution. After some times, we can see that the GAMS find the final solution or final NMI solution for this for this instance in a time that is around 20 seconds. Now we for this optimization, after we have the variable z, which was the objective function, and also variable x, where this variable shows that which equipments have been assigned to which factories. For example, here the equipment 1 and equipment 2 and equipment 4 and equipment 6 are all of them have been assigned to the factory 4, and equipment 3 and equipment 5 have been assigned to factory 11. And the rest are for other variables where, for example, at the end we can see that the equipments 19 and 20 have been assigned to the factory 4. So this is our variable. One question maybe here that regarding, for example, the implementation, the calling the parameters. Someone may call that if I want to use the Excel for calling the parameters, how can I do? I have another example here where if you want to uh, use the Excel, you can define the parameters like this, and then for each parameter you are able to call the Excel to that lets the GAMS software to take this to take the Excel file. It should be noted that if you want to call it from the Excel, you must put the Excel file into the project dir file. So after installing the GAMS, you see that there is a project dir and file from the GAMS dir file, and you can copy your Excel file here, and then you will be able to run your optimization problem here. So this code is not related to the GQAP. Let's back to the GQAP. So we see that how this the GQAP is implemented in GAMS software. Now let's us back to the slides. So the final step is the sensitive analysis. So the goal of sensitive analysis is to analyze the optimality, feasibility, and computational complexity. It means that we must analyze the factors which have a direct impact on the optimal solution. For our optimization problem, there are two main factors which have directly impact on the optimal solution. The cost factors in the objective function, the assignment cost of the equipments have a direct impact, and the capacity of the facilities or production centers have a different impact. So if I refer that from the model, the objective function, the parameters which are noted in the objective function, given in the objective function, are important. Another one for the capacity constraint, it also has it's very important because we can see how much it has a direct impact. So, for example, if we run this optimization problem again, we can see that there are, for example, some of the two factories which are very critical. The facility number 4 and the facility number 11 were critical because we can in display we can see that all of the equipments have been assigned to these factories. So for analyzing, we can change the capacity associated to these one. As you can see, for example, the capacity of the facility number 4 is too much, I think. So let's us change this capacity from 208 to 108, and then I do not want to change this. I only change the capacity for the this factory, if I reduce the capacity for for this factory, now I want to see that how much the optimal solution will be changed. This is an example. As I told you, can consider the other factors which are related to the objective function. For example, the cost of the assignments, the assignment cost for the equipments to the factories, and also the capacity of others. The main reason that I selected the capacity for the uh, factory number 4 is that I saw that most of the equipments were assigned to this factory. Now I changed this factor, and you can see that changing this, reducing the capacity for this factory has a high impact. As you can see, the computational time has increased. For example, in the previous one, the optimal solution was taking around 20 seconds, and now you can see that around more than 1 minute that GAMS solver is running. Uh, let's wait for a few seconds, and I hope that we will get a solution soon. And now after we get the solution, we can check that how much how much the optimal solution has been changed. So the main goal of sensitive analysis is to analyze that how the optimal solution will be changed. For example, if you remember the original test instance, the objective function was around 7,000, but here the optimal value is around 9,000. And if we see the value of the assignment, you can now see that, for example, different uh, new factors have been cancelled. For example, the factors number 6 and factors number 13 are chosen, and the most of the equipments have been assigned to these factories. In the previous one, the factors number 4 and 11 were chosen. So this sensitive analysis shows that changing the value for factory capacity has a direct impact not only on the computational time, but also the objective function, and also it results to a new solution for the assignments of the equipments to the factories. Um, uh, I would like to thank you for taking your time for listening to this presentation. If you have any questions, I will be happy to answer you by emails. Thank you so much and have a great day.